Hello, this is Rudra Prasad Baksi presenting before you MIMO system with Alamouti STBC scheme. The overview of the project is as follows. To start with the MIMO overview, singular value decomposition, water filling algorithm, Alamouti STBC schemes, simulations, and then observations and conclusion. To start with the MIMO overview, we have known that there are different types of systems existing in the wireless communication, which depends upon the number of transmitting antennas and number of receiving antennas. There are CISO, MISO, CIMO, and MIMO channels. In MIMO system, we have multiple transmitting antennas and multiple receiving antennas, and hence the name MIMO. Let us consider a MIMO system having R receiving antennas and T transmitting antennas. Then the modeling of the system will be as follows. Y1, Y2 up to YR are the received signals at receiving antennas, and X1, X2 and X up to X3 are the transmitted signals at the transmitting antenna. N1, N2 up to NR are the noise signals at the receiving antennas. H11, H21, H22 up to HRT are the H matrix or the channel matrix, which characterizes the MIMO channel. MIMO concepts are based on three main points: the precoding, the spatial multiplexing, and the diversity coding. Moving on to another important phenomena in a MIMO system is the singular value decomposition, wherein the channel matrix is decomposed into singular values to attain certain feats. Here we have considered that there are equal number of transmitters and receivers, which are equal to T number of transmitters and T numbers of receivers. So the singular value decomposition of the channel matrix is given by U sigma V Hermitian, and for sigma 1, sigma 2, sigma 3, these values are the singular values. The conditions for singular value decomposition is Uy mod square should be 1 and Uy Hermitian into Uj should be 0 if I is not equal to j. Again, Vi square or the mod square should be 1 and Vi Hermitian into Vj should be 0 if I is not equal to j. V and U matrices should be unitary matrices. Sigma 1, sigma 2 up to sigma t are known as the singular values, and they should all be positive and ordered, means sigma 1, sigma 2 up to sigma t should be decremental, and this order should be strictly followed. If all the conditions are satisfied, then we have the decomposition value of the channel matrix as H bar equal to U sigma V Hermitian. After singular value decomposition takes place, we have the model of the entire system as Y1 tilde, Y2 tilde up to YT tilde as the received symbols at the receiving end, and X1 tilde, X2 tilde up to XT tilde as the transmitted signals from the transmitting end. We find that Y1 tilde depends on the X1 tilde and N1 tilde. Similarly, Y2 tilde depends upon X2 tilde and N2 tilde, and so on up to YT tilde depending upon XT tilde and NT tilde. So this gives an idea, or rather a logical idea, of logical beam formation, that the receiver receives the symbols from the corresponding transmitter. For example, if transmitter 1 is receiving symbol, then it is transmitted by transmitter 1, and if transmitter T is sending any symbol, then it is received by receiver T. So a logical beam is formed in the entire system, and spatial multiplexing is taking place. Another important thing in a system is power allocation to the channel. The total capacity of the channel is given by the channel limit theorem, and that is equal to summation of I equal to 1 to t log of 2 1 plus pi sigma n square by sigma n square, where sigma n is the noise power and sigma I is the singular value of the I channel in the channel matrix, and pi is the power of the I channel in the channel matrix. Now, to have optimal power allocated to each of the contributing channels, we have found out by Lagrange's multiplier method, and following the water filling algorithm, it was found that any value of the power exceeding the threshold, that is 1 by lambda, then the power of that channel will be taken as 0, and any channel having power less than the threshold 1 by sigma will have optimally allocated power. Now moving on to the Alamouti space-time block coding in 1x2 system. It was first proposed by Alamouti, wherein two transmitting antenna sending symbol to a single receiving antenna. Here the symbols are sent from two transmitting antenna to a single antenna in two different time instants. In the first time instant, the symbol y1 is received, and it is equal to the channel matrix, and that symbol transmitted by transmitter 1, that is x1, and the symbol transmitted by transmitter 2, that is x2, plus the noise at the receiver end. And in the second time instant, the symbol y2 is received, taking the assumption that the channel matrix remains constant during the time interval, and according to the Alamouti scheme, the symbols which are transmitted are minus x2 conjugate and x1 conjugate plus n2 as the noise power at the receiver end. So the entire system of 1x2 system using Alamouti STBC is modeled as y1 and y2 conjugate, which are the received symbols in two different time instants, the H matrix, H1, H2, H2 conjugate and minus H1 conjugate, and the transmitted symbols X1 and X2. So it is found that in this way the entire Alamouti STBC 1x2 system is modeled for two time instants. Now W1 and W2 are the beamformers. They are required for decoding the symbols transmitted in transmit instant 1 and in transmit instant 2 respectively, and their values are given in these two equations. For example, to decode the symbol given in transmit instant 1, we multiply the W1 Hermitian with y bar, which is the total transmitted symbols received in both the time instants, and we found that ultimately it comes down to h double bar x1 plus n tilde. That means in time instant 1 the received symbol is decoded and is dependent upon the symbol transmitted by transmitter 1, and similarly it will be found that if in time instant 2 the received symbol is dependent on the transmitted symbol by transmitter 2, and h double bar is given as h1 mod square plus h2 mod square whole root under. Now moving on to Alamouti STBC 2x2 system. Herein Alamouti scheme has been applied to two transmitter and two receiver systems. In transmit instant 1, y11 and y21 are received at receiver 1 and receiver 2 respectively. This H matrix gives the channel matrix in time instant 1. X1 and X2 are the transmitted symbols from transmitter 1 and 2 respectively, and N11 and N21 are the noise powers at receiver 1 and receiver 2 respectively in time instant 1. In time instant 2, the received symbols are Y12 and Y22 at receiver 1 and receiver 2 respectively, taking the assumption that the channel remains constant during the time intervals, and according to Alamouti scheme, the signals which are transmitted in time instant 2 are minus x2 conjugate and x1 conjugate. N12 and N22 are the received noise power at time instant 2. Now with some rearrangement and modifications, the entire channel the entire system for both the time instant has been modeled as Y11, Y21, Y2 conjugate, Y22 conjugate, which are the 4 received symbols, and this is the channel matrix, and these are the transmitted symbols from transmitter 1 and X2 from transmitter 2, and these are the received noise powers at the receiver end in both the time instant. The channel matrix H is given by H11, H12, H21, H22, H12 conjugate, minus H11 conjugate, H22 conjugate, and minus H21 conjugate. Now moving on to simulation, we subjected both the systems which have been discussed earlier in a Rayleigh fading channel using the BPSK modulation technique. So we started with a Rayleigh channel BER performance of various theories including AWGN theory, Rayleigh theory, and Rayleigh simulation theory. Now simulating Alamouti 1x2 system and comparing with the MRC scheme with 1 transmit antenna and 2 receive antenna, we found that the bit error performance of Alamouti scheme, though better than the classical 1 transmit and 1 receive antenna, but approximately 3 dB poorer than MRC 1 transmit and 2 receive antenna. So Alamouti 1x2 system performs poorly as compared to the MRC system in this case. Now moving on to Alamouti 2x2 system, there has been a dramatic enhancement of the bit error performance of the system. The 2x2 system has a better BER performance as compared to the MRC 2x1 system. Now the observations are the performance of MRC with 1 transmit and 2 receive antenna is about 3 dB better than Alamouti space-time block coding with 1x2 system. The performance in Alamouti space-time block coding in 2x2 system is better than the 2x1 MRC system, as well as the Alamouti STBC with 1x2 system. Now it has been observed that the diversity order of Alamouti STBC with 2 transmitting antennas and R receiving antennas is 2R. Both in 1x2 and 2x2 systems using Alamouti STBC, there are no cross error observed. Noise in both cases are white noise. To conclude the entire project, we can say that the MIMO systems with pre-coding, spatial multiplexing, diversity coding, singular value decomposition, and water feeding algorithm has been elemental in increasing the data rate and reduction in transmission error, and also controlling the transmit power and without increasing the bandwidth. Alamouti STBC in 2x2 system has a better BER performance as compared to Alamouti STBC in 1x2 system. It also gives the freedom to have receive diversity and also transmit diversity without the knowledge of the channel state information. Now these are some of the reference. attention.